Okay, we're going to continue our discussion of calculating expected value and using that to optimize decision making. So in our next scenario, we're going to consider the video game Mario Party, where players move around the board by rolling a six-sided die to determine how many spaces they move on their turn. So essentially, this is a video game that represents a board game where you have players that move around the board, and different spaces on the board have different effects, and you gain or lose different things. And the way you determine on your turn how far along the board you move is by rolling a six-sided die, and whatever the number on the die that appears is, that's how far forward you move. So, suppose that a player can choose to roll a standard die, so standard six-sided die labeled 1, 2, 3, 4, 5, 6, or a special what's called daisy die, whose sides are numbered 3, 3, 3, 3, 4, 4. Okay, so the player has the choice. They can either roll a typical six-sided die, 1, 2, 3, 4, 5, 6, or they can roll the special die that four of its sides contain the number 3, and two of its sides contain the number 4. So our first question is, what is the expected value for the number of spaces moved for each die? And we've already calculated the expected value for a standard six-sided die. But just to quickly go through it again, we're just going to take the value of each outcome times its probability. Each of the six sides are equally likely. They each have a probability of 1 in 6. And so the value of the side with a 1 is 1, and it's got a probability of 1/6. The value of the side with a 2 on it is 2. It's got a probability of 1 in 6, and so forth. Sorry, this should be addition here. And then plus 6 times 1/6 for the last possible outcome. And so we just have 1 plus 2 plus 3 plus 4 plus 5 plus 6 over 6. That summation gave us 21 over 6, which is equal to 3.5. So the expected value for the number of spaces we'd move by rolling the standard die is 3.5. Now, the special die, what changes is there are four sides that tell us to move 3 spaces. So the value of those sides would be 3, and the probability of getting one of those would be 4 out of 6. 6 faces to the die total, 4 of them read 3 on them. And then plus, the value of the other 2 spaces is 4, and the probability of getting one of the other 2 sides would be 2 in 6. So this is going to come to 3 times 4 is 12, plus 4 times 2 is 8 over 6, so 20 over 6. 20 over 6 is going to reduce down to 10 over 3, which is approximately 3.33. Okay, so the expected value of the standard die is 3.5. The expected value of the special die is 3.33. So a little bit more about this special die. In this game, you choose what character is going to represent your player, and depending on the character you pick, every character has its own unique special die that's numbered slightly differently than a standard die. So an example being 3, 3, 3, 3, 4, 4, as opposed to 1, 2, 3, 4, 5, 6. This calculation is pretty common for these special die. Most of them have an expected value of 3.33, so a little bit lower than that of a standard die. Okay, so suppose that it's in the player's best interest to move around the board as quickly as possible, meaning on their turn, they want to move as many spaces as possible on average. The question is, which die should they use? Well, this is as simple as just picking the die with the higher expected value. Again, expected value is telling you in the long run what the average value of each roll is going to be. So on average, the standard die is going to move you forward 3.5 spaces, whereas the special die would only move you forward 3 1/3 spaces. Since 3.5 is more, the standard die is the better choice if it's in our best interest to move as far as possible. So in that case, we should use the standard die. Now, if the object of the game was simply to move as far as we could across the board every turn, that would be a fairly straightforward game. And there are board games that function like that. I believe like Chutes and Ladders, the children's game, I think basically boils down to just try to get to the end of the board as fast as possible. But most board games have something, interesting that happens on different squares, and so it may not be our only incentive to move as far as possible, but instead we may want to target certain squares to land on. So let's bring some of that into the equation. So suppose if the player lands on the space 3 spaces from their current location, they gain a coin. And we don't need to know what the coin is. The coin is just some measure of currency in this game. Okay? But if they land on the space 4 or 5 spaces from their current location, they'll lose a coin. Okay, so wherever they are now, if they land 3 spots away, they gain a coin. If they land 4 or 5 spots away, they lose a coin. The question is, which die should they roll then if they want to maximize the expected value of coins gained on their turn? And we are going to assume that all other spaces result in neither a gain nor a loss of coins. Okay, so the idea is, just to give a little depiction, our player is at the space where they are initially in the turn, and there are a number of spaces ahead of them. And again, when they roll their die, that determines how many spaces ahead they move. So if they roll a 1, they'd move from their location to the first position. If they roll a 2, they'd move to the second position. If they roll a 3, they'd move to the third position, and so on. And I suppose I should draw 6 spaces, since the standard die at least is labeled 1 through 6. Okay, so our setup here tells us 3 spaces away, they gain a coin. So if they land in this third space, that's we'll write +1. They gain a coin if they land there. But if they land 4 or 5 spaces away, they lose a coin. Now, remember, our choices are the standard die, which is labeled 1, 2, 3, 4, 5, 6, or the special die, which had 4 sides with a 3 on it. Oops. And then 2 sides with a 4 on it. Okay, so again, and then any other roll, so if they move 1 space, 2 space, or 6 spaces, we're assuming they're completely inconsequential. So they have an expected value of 0. They do not gain or lose coins for landing there. So the question is, again, what is the expected value for each die in this scenario? And notice that, so when we defined expected value, we said a value could be assigned to each outcome. And I said that's very vague. We're not defining what that value has to be. It could be, monetary, for example, or it could just be the number of spots on the die, or now it's coins. And in the same example, earlier, we were talking about the expected value for spaces moved. That was the number on the die. And now we're talking about the expected value for coins. So these are separate values that we're calculating, even though we're still talking about the same thing. We're still talking about the dice that are being rolled. But the expected value that we're analyzing is now different. We're no longer as concerned with just moving as far as possible. We're concerned with getting as many coins as possible. Okay, so for the standard die, if we go to calculate the expected value here, the outcome of rolling a 1 has a value of 0, the outcome of rolling a 2 has a value of 0, and the outcome of rolling a 6 has a value of 0. Because again, those are the cases where the square is inconsequential to our coins. We don't gain or lose anything. So the only terms we have to consider are rolling a 3, which has a value of +1, and a probability of 1 in 6, or rolling a 4 or a 5, which has a value of -1 and a probability of 2 out of 6. So if we roll the standard die, there's 1 outcome, rolling a 3, that takes us to +1 coins, and 2 outcomes, rolling a 4 or a 5, that takes us to -2 coins. And so our expected value for the coins we'll gain or lose here is 1 over 6 minus 2 over 6, so -1/6. Okay, the special die, on the other hand, if we roll a 3, then we gain a coin. So the expected value for the special die, there are 4 possible outcomes of rolling a 3. So we have a value of positive 1, 4 out of 6 times. And then if we roll a 4, we lose a coin, so we have a value of negative 1, 2 out of the 6 times. So that's 4 out of 6 minus 2 out of 6. So that is going to be positive 2/6, which reduces to positive 1/3. So the question is, which die should we roll to maximize the expected value for coins gained? Well, in this case, we'd want to roll the special die, because the special die has an expected coin return of 1/3 coin on average, whereas the standard die has an expected coin return of negative 1/6. Okay, let's take a look at one more condition to make this a little more complicated. So suppose, in addition to the spaces described in part C, so the one we just did, so that was 3 spaces away we gain 1, 4 or 5 spaces away we lose 1. The space 2 spaces away from the player now sends them to a special minigame where 60% of the time they will win 5 coins, but 40% of the time they will lose 5 coins. Now the question is, what is the expected value of each die, and which one should they roll to maximize the coins gained? Okay, so here's the situation. Our player is starting on a particular space. I don't know why they're upset now, but it's accidentally drew a frowny face instead. So the 6 spaces in front of them are the ones we need to consider. And from part C, we had 3 spaces away we gain a coin, 4 spaces and 5 spaces away we lose a coin, 6 spaces away nothing happens, 1 space away nothing happens, but now we say 2 spaces away there's a special game. And on this space here, and I'm just going to represent the game with a big circle, there are 2 things that can happen. 60% of the time, we get plus 5 coins, and then 40% of the time, we lose 5 coins. Okay, so I don't want to go into trying to design a reason for this, but let's just say I don't know, a number between 1 and 5 is picked, and if a 1, 2, or 3 is picked, we win 5 coins, and if a 4 or 5 is picked, we lose 5 coins. Some reason why 60% of the time we win 5, 40% of the time we lose 5. Now, one thing to notice right off the bat is the special die is actually not affected by this at all, because the probability of rolling a 2 on the special die, let me go back up, recall the special die contained the numbers 3, 3, 3, 3, 4, 4. The probability of rolling a 2 on the special die is 0. So the probability of reaching this minigame, if we use the special die, is 0. So the special die's expected value, which was 1/3 right here, that's unaffected by this. So I'll note the special die still has an expected value of 1/3. Now let's talk about the standard die. What we need to do is assign a value to rolling a 2, because there is a probability of 1 in 6 that we're going to roll a 2, and we need to assign a value to that. The way we're going to assign that value is actually by calculating another expected value. So we need to calculate the expected value of rolling a 2, and then use that to calculate the expected value of using the standard die altogether. So basically, it's the expected value of the minigame. So the minigame has an expected value of gaining 5 coins, so positive 5, 60% of the time. So that's times, here, let me write this a little bit neater, so times 0.6 for 60%. And then losing 5 coins 40% of the time. So negative 5 times 0.4. So again, this is a sort of a expected value inside of an expected value. What is the expected value just if we roll a 2? So the expected value of the minigame. Then we will plug that in to our big expected value calculation. Okay, so this is 5 times 0.6 minus 0.4, which is 5 times 0.2, which comes out to a nice 1. Okay, so essentially, we can consider this space to be worth plus 1 coins, because even though sometimes we gain 5, sometimes we lose 5, the expected value in the long run is again 1. So now, for the standard die, Now we have to consider the case where we roll a 2 or 3, which is plus 1. And there are two possibilities there. Whoops, sorry, scrolled all the way to the top. Let's go back down here. Okay, so for the standard die, there are two outcomes, rolling a 2 or a 3, which net us plus 1 coin. So 1 times 2 out of 6 outcomes. And then we lose 1 coin if we roll a 4 or a 5 still. So negative 1 times 2 of the 6 outcomes. And both these terms are actually the same, so this expected value is going to come out to 0. So before, remember, without the square, the expected value of the standard die was actually negative. It was negative 1/3 of a coin. This is now a little bit better for the standard die. An expected value of 0 is going to be better than a negative expected value. But this is still less than the special die's expected value of 1/3 of a coin, so we should still be going with the special die in this situation as well.